first thing that we're going to talk about today is this isometry. And I know you guys think this isn't as important yet, but it is very important because on the test, if you have a very good idea of what this flow chart means and what the questions you have to ask yourself, you're going to be golden for all the types of isomers. All right, so, what's the first thing that goes in the top of the box? Well, we're dealing with isomers. So I think that kind of makes sense. This should be isomers. Okay, and we know what is the definition of an isomer. And an isomer, iso just means the same, but mer means many different types. So it's like something that's kind of the same, but there's many different types of it. And the real definition would basically be like chemical species that have the same overall molecular formula. So same molecular formula, that's kind of important. Same molecular formula, so that's like the same number of atoms, like same carbon, same hydrogen, same number of all of those, but differ some way. And that's kind of what these difference boxes are. So the first difference is, well, we can differ in, I guess in substitution. And we know what that means. That would be like something, instead of the butane looking like that, let's substitute, oops, sorry about that. Just sideways. FaceTime call, that's why I did that. So substitution, we could change that butane and make it, something like that. So we're changing the substitution pattern of our butane. Okay, so we took that off and put it over there. So this type of isomer name is going to be constitutional. And I talked about like how important, or the lack thereof, I guess, this type of isomer is. We're not going to go beyond heptane for your exam, and it's pretty easy. You just kind of guess and check, so nothing really beyond that you need to know. So the other difference, instead of substitution, was we're saying it could differ in the 3D arrangement in space, so 3D maybe arrangement. And I guess the first one we really talked about was conformational isomers, and that was the only one we talked about, but there will be more. And that's what the TBD means. So we'll get there, but it's not there yet. So as of right now, this is where we're at. We have isomers. We know about the substitution, which leads to constitutional isomers. We just touched on the conformational ones, which were all of those Newman projections. And today we're going to do another type of conformational isomer with the chair conformers. And the rest we're going to deal with next week. All right, so we're building, but just make sure you guys have a good idea of where we're at right now. Okay. Then I have a couple more warm-up questions for you guys. So converting these Newman projections to line angle. So I'm going to give you guys, what time is it, 12:04? I'll give you guys like 2 minutes to try and do these two. Like a minute problems, like probably more than enough time. So at 12:06, let's reconvene and check these answers. You guys should be pros at these at this point. In the meantime, I can answer any questions anyone has while you guys try these out. If anybody has any.
I missed the part of the diagram that's right of conformational. What does it say right there in that little box?
That's TBD, to be determined.
Okay, gotcha. Thank you.
Yeah, we're like doing that next week, so we're building.
Thank you.
Anybody else have any other questions about isomers so far? People notoriously hate isomers. It's really not that bad if you really understand what isomers are and what the difference is. I don't think it's that bad, honestly. All right, so we got 1 more minute, guys. Keep trying these. Remember what you guys have to ask yourselves. Essentially, if I see a staggered conformer, I know it's always the trans kind of orientation. And if it's eclipsed, it's always going to be the cis orientation. And once you get that framework, you just fill in, the substituents based on how you see them. It's pretty easy. Okay.
I just have a general question about your YouTube videos.
Sure.
So when do you upload? I'm not able to ever attend your office hours on Mondays due to my work schedule. So I was just wondering when you upload those so that we can go back, and work through those problems.
Yeah. So essentially, and I've had actually a lot of emails this past week about that. I had a problem last semester in the summer when I was uploading them right after each session, because I started getting 2 people in a call, in a Zoom call, and it was I don't really want to sit here and do this for only 2 people. I'd rather have people live with me. So what I do now is I basically just upload all of them the weekend before your exam to watch. So if you miss Mondays, I know it's tough because you work and you can't help that. I guess the best thing I could just tell you is to try and find another TA's office hours that work for you on Mondays and that they can cover whatever I'm covering that day as well. So you will be able to get them. They're going to be on the YouTube channel, but probably not until like the weekend before the exam. I'll do like one massive upload.
Okay, thank you. Yeah, I'm sorry if you said something about it. I just missed
Oh,
it.
no, don't worry. No, you're good. Yes, side note. No, why? Yes, Brian, everybody go outside today. I was on the scooter this morning just for fun driving around Depot, and it is so incredible outside. If you guys are in Gainesville, definitely get out there today. All right, it's time to go over these. Okay, so the first question, we have this, staggered conformer, and, that tells me that it's trans, okay? So how do I know it's trans? Well, just trace this kind of direction. So we start at the chlorine. We have to go up through the page and then up again. So that's up through the page and up again, all right? So what was here? Well, that was a chlorine. And what was up there? That was a CH3. So I think that's pretty obvious. We're always gonna have to draw these wedges and dashes. Okay, so if I'm looking at it from this perspective, on my right, it seems like, and let me draw that eye again, so you guys kind of know my perspective. It looks like on the right, I have this CH-CH32 group, and you guys should really know that that's isopropyl, like just off the bat. So that looks something like that. And then by proxy on the left side, we have CH3, so I'm just gonna leave that as the dash. I don't need to write CH3 explicitly. Actually, let me just do that because I did it over there. Then on the back carbon, it looks like I have another isopropyl group coming out on my right, so it would make sense to do that, and then a chlorine going into the page. And it's pretty much that simple. All right. So anybody have a question on that one?
I have a question, just like in general. So for the line angles, like the CH3 that's attached, we wouldn't really write that though because it's
Exactly. Yeah. So I was kind of that's why I didn't even want to write this one. It's better to do this and just leave them.
Okay. And the
Because it's
same thing.
understood. What was it?
Okay. And it'd be the same thing for like the hydrogen on the next one. Like you wouldn't actually
Exactly. Exactly. Yep. So actually, I'll do this. What was it? Sorry.
Oh, sorry. I was just gonna say I have a general question as well, like just about the line angle formula because I'm still trying to understand picturing it. So the thick dash that you said that's always gonna be on the right side.
Okay, so I don't like always because it depends on your line of sight. Because watch, the minute I do this and look at it from this way, they all appear on the left. So you can say always if it's like this. Every time you look like, I guess, towards the right, anything on a wedge will always be on the right of your Newman. But if you do it from the left, it will always be on the left side, if that makes sense. Kind of
So the wedge is always towards you.
Yeah, exactly. Wedge is always out of the page and towards you. So like essentially imagine the isopropyl group is like the pen that's like sticking out, and then the methyl group is this black pen and it's going into the paper. Like it's like a V. Like I guess it'd be like that. And this one's coming out at me and this one's going in, if that makes sense.
Okay, perfect. Yep. Thank you.
All right. So then let's do this one. So this one's clearly an eclipse conformer. So that means I'm going to trace it. So ready? Down through the paper. Oh, you can't really see. And then up again. Okay, so hopefully you guys saw that. It's down through the paper and then up again. Down through the paper, up. So that would be down through the paper, up. Okay, so what was the first one? Fluorine. And the hydrogen would be here. So whoever asked me that question before, you would actually have to draw the hydrogen here because if you didn't, it would be assumed CH3. So here you actually have to draw that explicit hydrogen in. Okay. Okay, so always draw the wedges and dashes. And then if you're looking at it from this perspective, we see that we have the CH3 on my right, so that would have to be a CH3 here. I'm just going to leave it as a wedge. And then the bromine into the plane. So bromine is in. And then here it looks like we have an ethyl group coming out, and then the methyl group going in. And that's your answer. And I think I heard a microphone unmute, so if anybody has a question.
Yeah, that was me. So when it's a staggered structure, it's always gonna like have the basic line angle formula for the top, and then Eclipse always has the bottom structure.
Yeah, yeah. I think. Are you talking about like trans versus cis? What you're referring to?
I'm talking about like the top one looked. I don't know like how to explain it. The bottom kind of looks like a bowl.
Oh, okay. This, yeah. So that
Yes.
is trans and cis. Like, so again, just to reiterate that, trans is just everything like you've already done. Like, you know, when you draw, like when you do nomenclature, you always draw it like that. But what happens with cis is one of those bonds is rotated. So like you might get something like that. So like I guess that's fine. The bowl, I guess, yeah. So the bowl will always be eclipsed. I love that. And then this kind of mountain one is always going to be staggered. If that makes
Okay,
sense.
sorry, I didn't realize that was like the cis and trans name of that.
Yeah. And we'll get to that next week too. I think I might be jumping the gun, but trans, you know, it means like opposite sides, and cis means same. So you can kind of see like, basically with respect to this bond, but all of these groups are kind of on the same side of it. That's why it's cis. And then basically, let's just say with respect to this bond, you can see there's one group over here and one group on the other side. That's trans. That's what it
Okay,
stands for.
so trans always correlates with staggered and cis always
Correct.
correlates with
Correct.
eclipsed. Okay.
You got it. Perfect. All right.
I have another quick question, if
Sure.
possible.
Yeah.
So, I know you were talking about like how we're supposed to like not like write CH3 for a methyl group,
Mm-hmm.
but like should we come into habit of not writing it? Because I always
Yes.
tend to write, okay.
Yes. Exactly. I mean, would you get marked off? No. Like again, you don't even have a written test. Like when we used to, you know, do paper exams, like, and people would write CH3, I would never take points off. Like, there's no point in that. Is it wrong? Yeah, kind of. You're supposed to like just know the rule, the conventions of organic chemists, but who cares? You know, we don't care. But, you know,
Okay.
that makes you feel better.
Okay, yeah. Thank you.
Yeah, but for professional reasons, I guess I would just tell you yes, like in the future if you can avoid it, but like, you know, bigger things to worry about.
All right.
Yep. All right, so that's the warm-up for today, and we are going to do one question on torsional energy, and I think we're going to jump into chairs after. Okay, so let me get my notes out. We are here. All right. So torsional energy is not a fun one, but it makes a lot of logical sense. So let me grab my calculator. So this is like, you're not going to get a calculator on the test, so we'll give you nice numbers. Sorry. We'll give you nice numbers and stuff like that, but something like this. Okay, so given the following molecule, calculate the torsional energy or the energy caused by rotation. So what does that mean? So we talk about like the fact that, you know, we can rotate around these sigma bonds beyond the scope of this class. Why? But we can. And what is torsional energy? Well, the torsional energy is the barrier to cause that rotation. Every kind of molecular dynamic interaction, dynamic in the sense of physics, meaning movement, any of those molecular dynamics is going to have some sort of energy cost associated with them. And we're going to kind of calculate that here. So how do I do that? Well, torsional energy, I'll just call this, I guess maybe let's call that TE, torsional energy, equals the energy of the unstable minus the energy of the stable. And I think you guys can kind of understand what that means. The energy of the unstable is probably going to be what name? What Newman projection? What's that specific name of the most unstable one?
Eclipse.
Yeah, eclipsed, but we want it specifically totally eclipsed. So totally eclipsed. So we want to find the totally eclipsed conformer, calculate the energy there, and then we also want to minus it from the most stable one. So the most stable one is going to be called the staggered or anti, but specifically I'm looking for anti. Yeah, that would be the good one. Anti-conformation. Okay, so you basically want to get the Newman of the totally eclipsed, get the Newman of the anti-conformation, calculate all the energies there, and subtract it. Okay, so let's kind of do that. Let's draw the Newman based on the line of sight that we've already been given. Okay, so this is my front carbon. I see I have a CH3 going down. I see I have a CH3 to my left. And I see I have a hydrogen to my right. Okay. Then on the back carbon, so this is carbon number 2, it looks like I have, you know, a CH2, CH3 group going up. It looks like I have a hydroxyl group coming to my right and a hydrogen coming to my left. Okay, so that is the current Newman projection that we have. So now there's a lot of groups. So there's an ethyl group on the back carbon, a hydroxyl group on the back carbon, and then there's also 2 methyl groups on the front carbon. So you may not know, like where do I start? What are the two worst groups? Is it the hydroxyl group that's the worst one on the back? Or is it the the ethyl group that's worse on the back? And it may not be obvious, but you can look to these interactions and it's going to tell you. So the eclipse interaction for the CH3 and the OH groups is 4.2 kilocalories per mole. That's a lot. So that's the most one. So clearly, if we have a methyl group eclipsed with a hydroxyl group, that's going to be, in the totally eclipsed conformer. That's going to be the worst one. So we want to basically rotate the back carbon such that we get this hydroxyl group on this methyl. And it also looks like a potential bad one would be maybe a methyl and an ethyl. So is there a way that I can rotate? I'm trying to think here to get the methyl and the ethyl. And yeah, I can totally see something. So what if I rotated, let me see. What if I kept, I'm trying to rotate it this way, give me one sec, this way. Yes, okay. So what if I rotated this hydroxyl group 180 degrees, okay? So I'm gonna keep the front carbon the exact same. And I'm gonna rotate the back carbon 180 degrees. So let me draw this in red. Okay, so 180 degrees. Okay, so what happens after that? So we get this hydroxyl group comes clearly all the way over there. This ethyl group comes all the way over here. And this hydrogen comes all the way over here. So you guys see that? What happens? And this should be CH3. CH3. And how did I know to do that? So this was a little bit trickier. This is probably the hardest question you could get for a Newman. And I saw right here that these were the two highest energy ones. So I wanted to make a Newman projection in a way that these eclipse interactions are present. And the way to do that was take this hydroxyl group on the back carbon, rotate it 180 degrees, and you align this hydroxyl with that methyl, like we see up top here, and you also align this ethyl with that methyl. So that becomes those two energy barriers there. So let's kind of add up all those, energy values. So here, CH3 and CH2CH3, that's this methyl ethyl line, is 4.0 kilocalories per mole. Okay, and then the CH3OH is 4.2 kilocalories per mole. And then those two hydrogens is 1 kilocal per mole, just based on the chart. And we made these numbers up. There's no truth to them, okay? I just gave you guys relative energy values. So add up all these numbers and you get 9.2. So 9.2 kilocalories per mole is the energy of the most unstable. So I'll just put 9.2 up there. Just following that so far? Is anybody confused what I did? Okay, good. So now we want to get a Newman projection where we have the anti-conformation. So let's think about that for a second. If, this CH3OH, eclipse interaction is the worst, I want to have a Newman projection where they are anti to one another. That kind of just logically makes sense. So is there a way that I can get these anti? Well, yeah, it kind of looks like here, well, I want CH3 and OH to be far away from each other. So what if I rotated this hydroxyl, instead of being 180, what if I rotated it 120 to where that ethyl kind of group is? Do you guys see that? Let me get a different color for you guys. What if I took this hydroxyl and rotated it to that position? So that's one, each, in between here, each of them is 60, if you're wondering where I get the angles from. So if I do 2 moves, that's 120. If I do 3 moves, it's 180, yada, 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 so forth. So essentially, I want to rotate the back carbon such that it is where that, ethyl group is. So let's draw that conformer. And I can almost guarantee you will have a question like this on your test. They're not hard, I should say, they are hard, but you guys can do it. It takes time, but you guys can definitely get there. So let's draw this back carbon. So essentially, if I rotate this hydroxyl, it looks like over here. So that would go up top. Then by proxy, that ethyl comes here. I know I drew that kind of funky. And then here is the hydrogen. Okay. So now let's calculate the energy barriers here. So we don't have, and if it's not listed here, it's not significant. It means the energy of those interactions is not that high. So Gauss interactions with hydrogens are very minimal because a hydrogen is a single atom. They're very far away from each other. So you can see that there's no interaction here. There's nothing. There's no interaction here, and there's no interaction here. Okay. Typically with those hydrogens, they're just tiny singular atoms that don't really do much. Okay. So those are good. But we do have this ethyl, I guess, methyl interaction, and that's the 1.2. And we also have another ethyl-methyl interaction over here, 1.2. And then we have a methyl hydroxyl interaction, and that's 1.1. Okay? So, and just something to keep in mind, kilocal per mole. So basically we assume everything has 1 mole, essentially. But if you look in this structure, you could have basically done, oh, the methyl-ethyl interaction is 1.2 kilocals per mole. This is a little bit of stoic here, kilocals per mole. And how many moles, or how many of those do I have? Well, I have 2 moles, or 2 of those interactions. And you could have just done that quick shortcut and saw that it was 2.4 for this kind of whole region, okay? But either way, it doesn't matter. You could be a little bit more intuitive, or you could have just done the 1.2, 1.2. So add up those numbers, that's gonna be what, 3.5, I think? 3.5, yeah. So that's 3.5 kilocals per mole. Yes, Caroline, what's your question?
So if we look at the conformer that you drew like first, like just from the line angle,
Yep.
I was thinking well, maybe, so when you're thinking anti, I thought they had to be 180 apart, but wouldn't that OH and that methyl group already be 180 there? And then you get the methyl and the ethyl apart too?
Okay, one more time and a little bit slower. Sorry.
Sorry.
You're good.
So looking at there, wouldn't,
This one. Okay.
isn't this the anti-conformer?
Why isn't this the anti-conformer? Let me see. OH is there. Let me see. Did I do something different here? 1.1 and CH3 1.2. Oh, I actually like that one better. Yeah. I totally agree with you. I like that one way better. So yeah, I'm not even looking at a key or anything. I'm just doing this from scratch. So essentially, you're right I'm happy I actually did this because this is definitely the line of thinking that you want to do. But you're right. There totally is another, we knew, like I guess our compass was we wanted to have CH3 and OH anti. And we had that here, which I didn't really see. And we also had it here. Okay, so these are 2 different conformers where your CH3 and OH are, anti. But which one was better? And that's a great find. I'm really impressed that where this CH3 and this OH is apart, and you kind of like minimize, all of them being on one side, which is a good thing. If you're separating them kind of from this diagonal, that's good because you're reducing all those Gauss interactions. So yeah, great find. I actually like this one better, anti. And the CH3 hydroxyl group would be 1.1, and the methyl alpha group is going to be 1.2. So that would be a total of 2.3, right? 2.3. 2.3, and that would be 9.2 minus 2.3, and that should be, I think, 6.9 kilocals per mole. Okay, so what does that basically mean? That means that we needed to, if you have the most stable one, which would be this anti one, I have to like give it like with a laser or energy or heat or something, 6.9 kilocals per mole of energy to get to that conformation. Okay, so it's obviously not spontaneous because you have to put energy in, and yeah, that's that. And why would you not count again? So yeah, I kind of explained that earlier. Why wouldn't we kind of count that? And if it's not in this chart, in terms of Gauss, like we don't see an OH hydrogen Gauss interaction or a methyl hydrogen Gauss interaction, so they're not important. And the reason that is we said that this hydrogen is a singular atom. It's very tiny, and it's also staggered already. So there really is no interaction with the electron clouds of a methyl and this hydrogen. There is no real interaction there. And Caroline, is there another question you have?
Yeah, so just for like the problems, like when we're trying to find the most stable, and like we're talking the Newman structure. So if we have this chart here, like we should see what's the most, or like if it's most unstable, then that's how we should try to draw.
Yeah, exactly. Yeah.
Right.
So that's a great point. these are hard. I know these are hard because like you're like, you see all these numbers, you don't really know where to start, but like this is your compass, like right here. When I immediately look to this chart and I'm like, what are my worst interactions? And you want to make a Newman where you get these worst interactions. And then once you get there, just do then you want to get a Newman that has the opposite, where they're far apart from each other. And I think that should be good enough, you know, and you just kind of trial and error it, you know? Yeah. So that's pretty much all I want to say about that. Anybody have any questions on Newman projections, either going from line angle to Newman or Newman to line angle, or this torsional energy thing? Those are like the 3 topics for conformational analysis of alkanes.
What should we know about conceptually how to understand torsional energy if we don't have a table, if we're just asked a question about it in general? Because
okay, that's actually
I was confused about.
Yeah, that's very fair. That's actually a good question. So when there are multiple substituents, and by that I mean we have ethyl, hydroxyl, we have methyl, methyl, there's a lot going on, we would have to give you numbers. But we could give you something like, I don't know, I'm just gonna make this up. We could give you like like butane for these. This is like the simplest thing I can think of, where there's only one group, and maybe not even butane. Let me do like chlorine, something like that. You know clearly, like out of all the substituents on the back and front carbon, chlorine is the worst on the back carbon, and the methyl is the worst on the front carbon. So conceptually, like we don't even necessarily have to, like, I guess, tell you values here, because we could just say like a conceptual question like torsional energy equals, and I have a feeling you guys kind of see what I'm saying here. Conceptually, without numbers and actual data, we could be like, draw the Newman here, that's like the most unstable. Like, you know, selecting them from a list of structures on your exam. I'm just trying to think about it as a formatting that you guys could have, minus the stable Newman. And you would have to like select like the image that goes in here, I guess. Does that kind of make sense about how we could do it like conceptually? And it would be like, if there's only one substituent on the front and the back that are bulky, it would be the one where they're eclipsed here. So the methyl and the chlorine are eclipsed. And then those are where they're staggered or anti. So that's kind of like conceptually what you want to do, I guess. Does that help?
Yes, thank you.
Cool. All right, so now we're gonna go to chairs. Everyone hates chairs. Like this is like the worst. Like I'm not even gonna lie. This is the worst part about this next exam. Everyone just hates the chairs every semester. So don't think it's like just you guys. Like it's notoriously like a very hard to individualize. Ugh, that is right. All right, so I'm gonna do kind of this demo with my models again. So I'm gonna flip to the other screen and you guys just take a break and just kind of watch me, okay? All right, so hope you guys can see me okay. Let me pin myself, cool. Hi, okay, so this is my, you know, ball and stick model. And I want to just kind of ground us on where we're at right now. So this is the planar depiction. I don't know if you can tell, but see how everything's in line. So on paper, whenever you draw those hexagons, a 6-membered ring like that, this is kind of what we're talking about. Sorry. So it's planar. Ignore these substituents for now, but it's planar. So it's 6 members in a ring and you're drawing it on paper. So that's equivalent to literally saying this. Okay, so when you draw this hexagon, you're drawing basically this, okay? And all these black, you know, atoms are carbons, and these are gonna be substituents that we talk about in a second. This does not really exist in real life, and that's kind of the whole concept of what a chair conformer is. This does not exist in real life. So when you draw those hexagons, that's fake, that's not real. Most of the things we teach you are not real, actually. They're all just theoretical, like, things, but they're not really real. Anyway, so we have this kind of 6-membered ring. And what happens is it adopts something called the chair conformer in space. And I want you to look at this. Are you ready? So what happens, how do I form a chair conformer from the planar portion? And I'm going to call this carbon number 1, where you see this kind of these substituents, purple and green. This black carbon is carbon number 1. What happens is this carbon number 1 gets puckered and pulled up. You see what I'm doing? I literally just pulled it up. And carbon number 4 with the blue and the orange ball, go Gators, goes down, okay? So that's how I formed the chair. Do you guys see a chair? Head goes up here, body goes here, and the legs coming down here. Do you see my chair? So this is how this is really what a chair looks like. Okay, do you guys kind of follow that? So when you draw those 6-membered rings that are hexagons, cyclohexanes, they're not really cyclohexanes, they're these chairs, okay? And we'll talk about why that is in a second, okay? You guys kind of follow this model. See how it's kind of a chair? I put my head up here, put my body like along here, and then my legs kind of hanging down there.
You mind doing that again, just so
Yeah,
I can
sure.
like again?
That works.
Thanks.
Okay, try it again. So now, again, flat. So how do I know it's flat? You look vertically, and I mean, whatever, do this way, and you see that all these, this is how you would draw it on paper, okay? You guys are used to this, okay? But this isn't real, and we'll explain that in a second. So what happens is carbon number 1 with all these, the purple and green, I guess, Hulk substituents, it gets pulled up. So we're pulling literally this atom, these bonds around this carbon number 1, and we're pulling it up. Like, do you see what I'm doing? I'm literally pulling it upwards. And then this one, this is carbon number 4, so it's always 1 and 4, and we'll talk about that in a second. This 4th one always goes down for now at least. Okay, so I literally pulled this one up, you saw, and I pulled this one down. And now I'm left with this chair. So if you can see it, like head would go up here, body goes here, and legs go down there. Kind of follow that?
Yeah, are you gonna go into like why, I guess?
Yeah, totally, yeah. All right, so now I'm gonna go back to paper and we're gonna explain the theory behind it, okay? Thank you, Hal. All right, I always have somebody to ground me back. So again, we have this, cyclic structure, the 6-carbon ring, okay? And, I'm drawing these hydrogens in here, and they're present on every carbon. So if I were to ask you, back to, your first exam, what is the hybridization of that carbon? Right? So you can say it out loud, put it in the chat box, whatever.
sp3.
sp3, great. You guys are pros at this by now. That's sp3. I saw 4 areas of electron density. Powers have to add up to 4. We're at sp3. Okay, what is the bond angle of sp3?
109.5.
Exactly, you guys are awesome. 109.5 degrees. Okay, what are these bond angles inside? Not 109.5, they're all 60. Or something like that. Or is it 120? I don't really know. Let me see. Let me check that one more time. It doesn't really matter what they are. It's just not 109.5 is the kind of planar. Let me look that up real quick. Cyclohexane bond angle. Okay, sorry, I meant 120. So all of these inside, I'll just redraw it down here. All of these inside are 120. Okay. And we talked about, ignore this top one. And we talked about how that's sp3 and this is 109.5 degree bond angles. Okay. So if my expected geometry is supposed to be 109.5, but this planar depiction says 120, do you guys kind of see how that doesn't make sense? So that's like the big kind of controversy here. Is like we draw it on paper as 120 degree bond angles, and that's not true. What it really is are these chair conformers, because these chair conformers move the bonds in such a way that you get to the 109.5 degree bond angle. And that's the whole concept of what a chair is. Anybody have an aha moment? So essentially, when we move carbon 1 up and we rotate these bonds away from this plane, and we put carbon 4 down and we push those bonds under the plane, we're arranging everything in such a way, like we're moving bond angles so that we can get to that ideal 109.5 degree bond angle. Okay, so that's kind of the theory there. All right, so how do I do this? So essentially, let me just do like a very basic example. Okay, and I'm gonna do, let me do this. Okay, so I'm gonna draw, this structure. This is my first example, okay? And notice how I'm gonna number around the ring, and I'm not numbering based on nomenclature. I'm just purely numbering the way that I feel like it, okay? So I decided just to name number carbon number 1. I mean, this is how you would do it for a nomenclature anyway, but point is 1 is up here and 4 is down there. So what am I going to do? Well, like I said, to make a chair, what happens is, this is planar, so everything is now in line, okay, flat, like this. What happens is, let's call this the bromine. This purple is the bromine, and this orange is the chlorine. So what you do is you pull carbon number 1 upwards, like that, and you pull carbon number 4 downwards, okay? So let's kind of imagine that. So I'm going to draw an arrow that says up, and I'm going to draw an arrow that says down, okay? And you guys are going to have to, you know, get better with drawing these guys, okay? But that's what a chair looks like. And I'm going to fill in, and that just takes practice, fill in these numbers. Okay, so I want to point something out to you guys. So right here, okay, if you notice, everything I boxed in this kind of red dashed line, 2, 3, 5, and 6 are all still flat, are still in one plane. And that was kind of obvious. I don't know if you can see this, but this is my chair right now. So do you see how 1 is kind of higher than, oh, sorry, I keep dropping it. So do you see how 1 is higher than 2, 3, 5, and 6? And do you see how 4 is lower? Okay, so 1 is higher, 4 is lower, but 2, 3, 5, and 6 are all kind of this square. It's still planar and in this rectangle. Everybody sees that before I move the model away? Hope. Okay, good. Okay, so keep that in mind. So literally, if I'm showing you this real life scenario, I'm pulling 1 up and I'm pulling 4 down, that should now make sense to you guys why this chair looks the way that it does. This is just a depiction showing 1 is up and 4 is down, okay? So what does that mean and in terms of the substituents? So let me draw in the hydrogen that's not here. Okay, so whatever I'm pulling up, so you can imagine that I'm going back to planar here. This is planar, and this is my bromine, and I literally am grabbing this and pulling it up. So what do you think is going to be the orientation of the bromine when I pull it up? Well, it's going to be axial, or sticking directly up. And if this doesn't make sense, I'm going to catch you with examples, don't worry. And whatever isn't axial is always going to be equatorial. So we have these kind of, now this term, axial and equatorial, that we need to talk about. So what axial means is it's to the axis, like, you know, the Earth rotates, you know, slightly at an angle on its parallax, but it's around this. Let me draw the Earth. Let me draw the Earth for you guys. So we have, you know, this would be 90 degree, but we're actually, you know, a little bit, I think it's like 20 something degrees or whatever. So we actually rotate around that axis. So axial just means kind of like perpendicular to this, you know, main surface. It's perpendicular to that main surface. So that's axial. And equatorial would be like the equator. So you guys know the equator of the Earth goes this way. You can see how that kind of resembles equatorial. Okay, cool. And that's me, ruler of the world. I don't know. Okay, so does that logically make sense? Based on, and I know we haven't really touched on much yet, but essentially I'm pulling the bromine up. So that would mean that it's axial and that hydrogen is equatorial. On 4, what did I do with 4? Okay, so instead of going up, I actually pushed it down. But now kind of think about, you know, I might be making you guys a little nauseous here, but so this is where we are, and this was the chlorine. And how do I know this was the chlorine? This is the chlorine because it's on a dash. So it's, you know, typically oriented away. So imagine looking at it from a top view, okay? So the dash tells me that it's down and into the paper. So this would be the chlorine, and the wedge tells me it's up and out of the paper. So that's hydrogen. Okay, so actually let me do it like this. This might be better for you guys. Okay, so this is equivalent to that. Do you guys see this? The hydrogen is this blue ball, and this chlorine is this orange ball, okay? So literally, what am I doing? Well, I'm pulling it downwards. Okay, so if I pull it downwards and I look at it from a side view, does that orange chlorine look equatorial or axial? It looks axial. So, and whatever is not axial becomes equatorial. Okay, so that is my first chair conformer. Okay, and we haven't really talked about much yet with that. Okay, so now I'm going to draw other things in that you don't have to, but this is going to help us with future examples. So what happens is there is a trend around this chair, and the trend is it's alternating axial up, axial down, axial up, axial down. Okay, so up here we're axial up. Here, whatever the substituent here is going to be axial down. So that would be you know, a hydrogen down. And, you know, there's also a hydrogen that's equatorial. But if we're axial down on 2, we should be axial up on 3. And then that means axial 4 should be down. Axial 5 should be up. Axial 6 should be down. Do you see kind of the trend? It's always up, down, up, down, up, down, up, down. Okay. Now the next thing, in terms of the stereochemistry. So let me just draw another example. In terms of the stereochemistry, such as, let me just do multiple things, so chlorine and bromine and fluorine. I'm just making things up. And let's call it like this. And let me just do like sulfhydryl, something random, okay? Wedges like to be up, dashes like to be down. So wedges equals up, and dashes like to be down. Okay, so this is kind of important. I would know that. Okay, I know I might be throwing a lot at you, but it's all going to make sense soon. Okay, wedges like to be up, dashes like to be down. And we basically want to check for this trend. Okay, so you probably are confused, but this will make sense. So let's draw that first chair for this one. And then number it. You always should number these so you don't get anything like misplaced. So that's my first chair. You guys can see that, okay? And let's look at carbon number 1. Okay, so in my chair conformer, I kind of now know the theory. So the carbon number 1, at least in this chair conformer, is pulled upwards like that, and carbon number 4 is pulled downwards, okay? So carbon number 1 is up, and that wedge likes to be up. So if the trend agrees with the stereochemistry, so that's what I'm looking at, does the trend, question mark, equal the stereochem, meaning the wedge or the dash? Okay. Yes, so the trend, which means it should be up in this situation, does it match my stereochem thing right here? Yes, it does. So what does that mean again? Let me repeat that. If the chlorine, which is supposed to be up based on this chair conformer, matches the stereochemistry like argument, the wedges being up, you make it axial. Okay, and that might be confusing, but you'll get me. On 2, since the trend says up, down, the thing on 2 should be down. Does the stereochemistry match what it wants to be? Yeah, it does. So that means I'm going to make it axial. 3, what is my trend? It should be up, okay? Based on up, down, up. Does the stereochem, meaning wedge or dash, align with being up? Well, yeah, we know wedges like to be up. So let's put it axial, okay? Now on 4 should be up, down, up, down. So whatever on 4 should be down. Does the stereochem match the trend? So no, we have a wedge that should be up, and the trend says we should be down. If I am having a conflicting life existential crisis, it's not axial, it's actually going to be equatorial. So if it doesn't match this argument, it's going to be equatorial. No teacher will teach it to you this way. This is Stephen's way of teaching it, but you will always get it right. Do you guys kind of follow what I meant by trend and you know, the stereochem, yada, yada, yada? That's amazing. Yeah, I'm happy like that.
I have a question.
Sure.
So for the other one, like for the other molecules you're to the left with the bromine and the chlorine only,
yeah,
for the chair conformer, when you were going like up, down on there, I guess it's getting confusing, but it's also like a lot of hydrogens instead of, you know, so is that different or?
No, this is the exact same. So that's, we can kind of, you know, confirm, you know, that we drew the right thing based on what we just kind of talked about with all these rules. So let's just look at that. So you know, in carbon number 1, we pulled it up. That's based on this picture. Like you can just see 1 is above the plane. We've already talked about that. So does the stereochemistry, meaning the wedge or the dash, match what our trend was? Our trend says up. So yeah, the stereochem of that bromine is a wedge, and we know wedges like to be up. So yeah, if it matches, we always make it axial. So I guess we could say if it matches like this equal sign, it's axial. If it doesn't match, it would be equatorial. Does that kind of make sense? Oh, you can't see that. So I wrote this like line through it. If it doesn't match, it's equatorial. If it does match, check mark, it's axial. I know my sloppy notes, but yeah. Okay, so then go to 4. So our trend says up, down, up, down. So does the stereochemistry on 4, meaning the dash, like to be down? Well, dashes do like to be down, so make it axial. It matches the trend. All right. The hydrogens, it doesn't really matter because they have the same, you know, same identity, so there won't be really anything to really see there.
Quick question. So for number one, let's say we have bromine and then we have hydrogen. So they both have to go up. And since hydrogen doesn't go up, I mean, it has to go up, then, I mean, it's a dash, so it has to go down, then that's why it's equatorial, right?
Say that one more time, sorry.
So on number one, we have bromine, which is a wedge, and that goes up. So
Correct.
it's axial. And then since hydrogen, it's a dash, it's supposed to go down. So it's equatorial. But it's
Exactly.
like they both go up on substituent number one.
They don't both go up. So I mean, you're rotating the, so watch this. So watch this model. So this would be like, let's say the purple is the bromine and the green is the hydrogen. So like, I guess you can say that like when you pull this carbon bond up, they kind of both move, but you see how like the purple is sticking directly up. This was the bromine, and this is kind of still oriented a little bit downwards. Okay. So that's kind of why we did that. Do you see that?
Okay. Yeah, that makes sense.
Yeah. Good.
Thank you.
Okay. Yeah. So then the next thing is we're going to talk about is this thing called a ring flip. Okay. So instead, let me go back to, my computer and I'll document Cam in a second. So hold on 1 second. 1 second, Caroline. All right. Yep. See you, Abby. Okay. So we're back to here. Can you guys see me? I mean, I can't even see myself. Oh, here we go. Okay. So we're back at this planar depiction. Okay. And we've been saying this whole time that, like let's just say the purple is the bromine and this orange is the chlorine, okay? And what we did last time was we took this planar picture, okay? And what we did was we pushed it up and we pushed the fourth one down. But what if I did the opposite? So instead of pulling one up, let's push one down, okay? And then let's push 4 upwards, okay? That's what a ring flip is, okay? So you can basically start, let me go flat again. You can start with like, let's say, oh, I want to put carbon number 1 up and carbon number 4 down. Okay, so that's one structure of your chair conformer. And then there might be one where 1 is down and 4 is up. Okay, and that's the other chair conformer. And we're going to talk about stability with these and see which one is better, just like which we did with Newman projections. Okay, but what's the consequence? So maybe before we saw, with that first one, bromine was up and that was the purple one. But now what happens? It looks like the chlorine became axial. So remember before, purple was axial, and that's the bromine. But now when I push it down, do you see how it becomes equatorial? And this is the axial thing. And the same thing for the chlorine. So in the original one, when we pushed 4 down, and this one was up, this was axial chlorine. But in the ring flip, now this became axial, and this is now equatorial. So that's a very important find for your chair conformers. And I'm going to go back to the document camera. Right. Okay. So what does that mean? So in a ring flip, I guess I'll just draw it up here. Ring flips. Okay, ring flips. So essentially, I can't even see this. Where'd I go? Let me pin me up here. In a ring, actually, let me go nicer. Let me give you a better paper. Okay, so in a ring flip. Okay, so we start here, planar, okay? And I'm gonna draw this example. Let's just do BR, and let me just do this one. So let's just do something funky. Let's do maybe a carboxylic acid or something crazy like that. Okay, so in a ring flip, so let's just draw the first conformer, okay? So the first one would be, let's just say the first chair I want to draw is with 1 up. That's kind of like the first one I always do, is where I put carbon number 1 up and carbon number 4 down. So carbon number 1, if I pulled it up, that substituent wants to be axial up. Does the stereochem on carbon 1 match being axial up? And we said yes, wedges like to be up. So then if it matches the trend, let's draw it axial. By proxy, the hydrogen would be on an equatorial position. There's nothing on 2, there's nothing on 3, but let's look at 4. 4, the trend says up, down, up, down. So whatever's on 4 should be axial down according to my trend. Does the stereochem on 4 match that trend? No. Dashes like to be down, not wedges. So if it does not match, you make it equatorial. Let me just do CH2, and this is the abbreviated version of that. Okay, CH2, COOH. Okay, so does everybody kind of follow that? That's how I got this chair conformer. Then I want to do the ring flip. So we have this kind of equilibrium arrows, okay? Because they're rapidly kind of interchanging between each other until they get to the dynamic state equilibrium. But essentially, instead of 1 being up, now 1 is down. And instead of 4 being down, 4 is now up. So this is what this chair conformer looks like. Okay, so we're here. So notice, remember I talked about that whole thing with this being the plane, and that's still a plane, that's flat like a square, and now 1 is below it and 4 is above it. So the new trend is what's on 1, yeah, see ya. So what's on 1 is actually going to be down. So does the stereochemistry on 1 match being down? No, it does not. So 1 now has an equatorial bromine. But you can also now just analyze the hydrogen. 1 needs to be axial down. Does the stereochemistry of the hydrogen match that trend? Yeah, it does. That's why it's axial. Okay. Nothing on 2, nothing on 3. Let's look at 4. 4 is clearly up. And if you don't know it's up, you can just look at the trend. Down, up, down, up. So on 4, we should be up. Does the stereochemistry on 4 match being up with respect to this kind of like carboxylic acid functional group? Yes, it does. So let me just draw axial up. It's CH2, COOH. And then let me just analyze maybe the hydrogen by itself. That hydrogen should be down. Does the stereochemistry up here match that? No, so it has to be equatorial. So let's kind of just look at these two structures in comparison. On carbon number 1, the bromine was axial, and now on the second conformer, it's equatorial. On carbon number 4, in the first chair conformer, that carboxylic acid group was equatorial, and then now in the chair conformer, it's axial. So something very important to note in ring flips is axial things go to equatorial, and equatorial things go to axial, okay? Always in a ring flip. And that's another great find that you have there. And then I have one more thing I want to talk about. Okay, so is anybody confused on what a ring flip is? It's just instead of 1 being up and 4 being down, maybe 4 being up and 1 being down would be better. And then we're going to rationalize maybe, is the left one better or is the right one better? Yes, Caroline, what's your question?
So I mean, I get the idea that the ring flip is like, okay, so instead of 1 being up, then it would go down, and then 4 being down, it would go up. But so when you're comparing like the trend with like 1 being up and 4 being down, are you looking for, like, do you just look at if it's a wedge or a dash, or are you counting like an order? Because you went like up, down. So
yeah. That makes sense. I'm sorry, I didn't mean to cut you off. Was there anything else to that?
No, that's my question.
Okay, so essentially, when I'm saying up, down, I'm just talking strictly about the axial substituents. And it always is the same. So like in this chair conformer, it's always from carbon number 1, axial up, axial down, axial up, axial down, axial up, axial down. Okay, always. And this one, because just from the way that it looks, it's axial down, axial up, axial down, axial up, axial down, axial up, always around the ring. When I'm asking, like, so that's the trend, what I just said. Now, we need to know, does the stereochem, this wedge dash, match that trend? So in 1, that needs to be axial up. That's just based on the trend. That's just what we know to be true. So does this, substituent on carbon number 1 have that stereochem to allow it to be axial or follow that trend? And yes, we're looking at this wedge. So this wedge is typically up. So if our trend says axial up here, that's consistent. Let's leave it up. But this hydrogen is not, in that orientation. It does not follow the stereochemistry of what our trend says. So it has to be equatorial. Okay. That's kind of what I'm doing with matching the stereochem to that trend. Does that make more sense? Oh, okay, so it's a trend of up, down for the chair conformer and not the planar one. Correct. Exactly. You got it. Okay, so let's kind of just talk about one more thing with theory, and then we'll be, oh my God, I just did all theories here. But that's okay. That's important. You guys know all this. So one more thing. So now we're going to talk about stability and how to answer these questions. So let me take one more example. I'm really just winging this. These problems aren't anywhere. I'm just kind of making them up. So hopefully you guys are writing this down. Okay, so let's talk about which chair conformer would be better. Okay, so I just drew this kind of methyl cyclohexane. It's a very simple structure. And let me draw my first chair conformer where I made 1 going up and 4 going down. So 1 we know by the trend says axial up. Does the stereochemistry of that methyl group match going up? Yes, it does. And that's all I need to draw. And then in my next chair conformer, 1 is down. Okay, so I know based on what I just showed you above, the axial thing becomes equatorial. I'm not even gonna go back to that structure. And that equatorial thing becomes axial. Okay, so that's literally all I needed to know. So now in terms of stability. So there's something called 1,3 diaxial interactions. I know, really crazy name, but we'll break it apart. 1,3, meaning something on the 1 position and something on the 3 positioning. So that's di and axial, so probably 2 axial groups, maybe 1 on the 1 and 1 on the 3, are gonna have these interactions. What does that mean? So let's go this way. 1, 2, 3. What is my trend? Well, up, down, up. So there definitely is a axial hydrogen upwards. Okay. And then maybe if I, from this carbon backwards, let's go 1, 2, 3. Yeah, there's definitely an axial up hydrogen here as well. Okay. So what is a 1,3 diaxial interaction? Well, it's something on the 1 carbon and then something, at the 3 position, on either side. And the electron clouds actually eclipse with one another and they all interact. Okay. And again, it's that same repulsive argument, the electron clouds. So 1,3 diaxial interactions are bad. Not good. These are not stable. But notice when it's in, this chair conformer, we don't have this methyl group eclipsing with anything like that because these are called diaxial interactions. So in terms of stability, anytime we're going to rationalize which one is better, we prefer the large groups, large bulky groups, prefer to be equatorial. Does that make sense? These large bulky groups, now it makes sense why they want to be equatorial, because in this situation, you reduce these hydrogen diaxial interactions because it's equatorial. You can't have diaxial interactions when it's equatorial. So when we're talking about stability, it's a very, very good idea to just look at a chair conformer where you make this large sterically hindered group on an equatorial position. And that's typically the most stable is this side. So this would be the most stable chair conformer. And maybe I can even take it a step further is, where does the equilibrium lie? Does the equilibrium lie to the left or to the right? Oops. Same thing with acid-base chemistry. Just remember back to that. We always lie to the side where we are right. Yep. More stable. Yep. More stable. Love that. So we're always going to lie to the more stable side, which means we're going to lie to the right on this side. Okay. So I think that's literally all on chair conformers. And today was very conceptual, but I'm actually really happy with that because honestly, this is a very visual, difficult, thing to see and rationalize. But I think we did a pretty good job today. How do you guys feel overall? If you guys want to say out loud or in the chat box? Good. Okay, that makes me feel good. Good. Better than you were before, hopefully. Okay, awesome. All right, so we're gonna meet next Monday. And next Monday, I think on the agenda, you guys don't even have anything more this week, I don't think, in terms of new material. I think Friday's lecture is just gonna be some new stuff. Not some new stuff, excuse me. So on Monday, we will just basically recap all of this, and then we'll talk about the other types of isomers in this tree. So one more thing I just want to add here, back to the beginning today. So there are 2 types of conformational isomers that we have seen now. So we have seen Newman projections, so Newmans, that's one of them. And the other ones are now chairs. Okay, so that's kind of where we're at now. We just added this extra one today, chairs. And then next week on Monday, we're going to talk about the last type of isomers, and that's here and here. Okay, and that's it. So have a good weekend. You guys keep studying this stuff. You guys are doing great. And I'll see you guys on Monday.
Thank you.
Yeah.
Thank you.
Thank you.
Yes,
Yeah.
I have a quick question.
I have a question.
Sure.
Yeah.
Oh yeah, sorry. It doesn't matter.
Whatever, I don't care.
You can go.
Okay, so is it always carbon 1 and 4, that'll go up and down?